Hey there everyone, this is Zare, and we're back with Advent of Code. So, it's a bit of a mess last time, so did a bit of cleanup for us. First of all, that problem that I was getting with day 20, we can't remove the entries, because when we remove the entries, the indices all get scrambled up, and so we can get false positives and all other sorts of nasty stuff. So once we removed that problem and we null them, things fix themselves up. As for day 21, mostly I was overloading my cognitive space without properly spacing things out. I trashed what I had, broke down into the steps that I needed to perform, and then created a subtask for each. In fact, looking at these now, I should probably extract these and make functions out of them. So let's go ahead and do that now. I also extracted these commands out, just so that we know what we're getting into each time we call it. Okay, so what we're going to need to pass in, we're going to need to pass in the subgrid count, square root, put in the size, X and Y are all in there, and we're going to need the grid. So that's going to be array of string grid. Do we need this anywhere else? Nope, so we can just calculate that inside. Don't need that. Okay, so that's good. Translate subgrids into their replacements. So this is going to return subgrids. Yep. We're going to need the subgrid count square root, subgrids, anything else we need? It's made in there. I think that's probably enough. delete. So we need that. So what is replace grid? It's an array of strings. I need to put in the replace subgrids. I think that's probably okay. We'll find out in a bit if that's wrong. You're an integer. Okay, so why aren't you happy? Fractalize. Okay, you should be that. Oh, and you were misspelled. And just a bit of code style here. I prefer to have my submethods after the main one. Let's take a look. We're iterating twice over the basic pattern using the that. Yep, all tests passed. So that looks good. Is that what we expected? Yep, that's the grid we expected. Okay, so next up, our test is no longer going to work. Because we need to go 5. Let's test it out. We came up with 155. Correct answer. All right, so what's the twist? How many pixels stay on after 18 iterations? Oof. So hold on, let's... So we start with a 3 by 3. And if we... Aren't you uncommenting? Oh, that's why. Good reason. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So over 5, we went from 3 to 18. So that's going to expand pretty quickly. Okay, well first let's clean up our solve here. So we're just going to have an iterations variable. confirm that still works. 155, yep. So the theory is that this is going to just explode with 18 iterations, and we're going to have to wait several hours to get our solution, but let's just give it a try. That actually wasn't so bad. But is it the right answer? Yep, okay, that works. So it did take us 3.95 seconds, which isn't terrible. I just want to do a quick mental exercise to see if there are some ways we might be able to improve that. So we could try to detect any loops that end up happening because of the rules. Though with only 18 iterations, we'd have to get pretty lucky with the rule set to find ourselves in any of those. I don't think, based on the input, that we can do any reductions into numbers. And we kind of do have to keep filling up the space, because if we don't fill up the space, by making that fractal picture and keep on expanding it, we're going to end up with, well, we have to do it from scratch each time we do an iteration. Which you would skip all the iterations before the last one, and you're right back at square one. You could convert all of these into numbers. That would probably be the solution here. Though you'd have to use some bits to determine what the size of the grid is as well. As for instance, you could treat this right here as 0. Oh no, it gets more complicated because you can rotate. Yeah, so even if we said that this was 0 and this was 1, well, let's get into this one here. Well, maybe you can still do this, because they can't give us any rules that would be rotatable or flippable. Otherwise, those rules are just dead in the water. So you could say that this is 0, this is 1, this is 2, this is 3. Next one's 4, the next one's 5. Yeah, you might be able to pull it off just converting these into numbers and running hash functions. But it sounds like a lot of work to shave off 3 seconds. So let's commit that. No, I don't want to. How do I change my text? Don't know why this has suddenly become uppity. Okay, Sporifica virus. Diagnostics indicate that the local grid computing cluster has been contaminated with the Sporifica virus. This does not seem to be a real thing because they're not giving us a link. A grid computing cluster is a seemingly infinite two-dimensional grid of compute nodes. Each node is either clean or infected by the virus. To prevent overloading the nodes, which would render them useless to the virus, or detection by system administrators, exactly one virus carrier moves through the network, infecting or cleaning nodes as it moves. The virus carrier is always located on a single node in the network and keeps track of the direction it is facing. To avoid detection, the virus carrier works in bursts. In each burst, it wakes up, does some work, and goes back to sleep. The following steps are all executed in order one time each burst. If the current node is infected, it turns to its right. Otherwise, it turns to its left. If the current node is clean, it becomes infected. Otherwise, it becomes cleaned. It's done after the node is considered for the purpose of changing directions. The virus carrier moves forward one node in the direction it is facing. Diagnostics have also provided a map of the node infection status, your puzzle input. Clean nodes are shown as dot, infected nodes are shown as hash. This map only shows the center of the grid. There are many more nodes beyond those shown, but none of them are currently infected. The virus carrier begins in the middle of the map facing up. For example, suppose you're given a map like this. And the middle of the infinite grid looks like this, with the virus carrier's position marked with brackets. It's on a clean node, so it turns left, infects the node, and moves left. It's on an infected node, so it turns right, cleans the node, and moves up. 4 times in a row, the virus carrier finds a clean, infects it, turns it left, and moves forward, ending in the same place and still facing up. Okay, so we make a square there. Now on the same node as before, it sees an infection which causes it to turn right, clean the node, and move forward. For the above actions, a total of 7 bursts of activity have taken place. Of them, 5 bursts of activity caused an infection. After a total of 70, the grid looks like this, with the virus carrier facing up. We made a spiral. By this time, 41 bursts of activity caused an infection, though most of those nodes have since been cleaned. For a total of 10,000 bursts of activity, 5,587 bursts will have caused an infection. Given your actual map, after 10,000 bursts of activity, how many bursts caused a node to become infected? Do not count nodes that begin infected. Okay, that's not too bad of an input. Okay. So we've had to deal with infinite grids before. And for that one, we just cheated and gave ourselves a finite grid to work with. We could do a two-dimensional dictionary. That would help us create our map. And that should be maybe a bit slower than a two-dimensional array, but at least we'll have it expandable. But it might be just as efficient as a two-dimensional list. Actually, Dictionary is based on a hash table. That means it uses a hash lookup, which is a rather efficient algorithm to look up things. On the other hand, a list, you go element to element until it finds the result from the beginning. Each time. There's a more or less fixed lookup time. This is hashing to search for the data. Dictionary first created. Blah, blah, blah. Each step that lookup takes more and more time. Hash value for the key, and this hash value leads to the target data bucket. After that, each element in the bucket needs to be checked for equality. But actually, the list will be faster than the dictionary on the first item search because nothing to search in the first step. In the second step, the list has to look through the first item and then the second item. So each step the lookup takes more and more time. The larger the list, the longer it takes. Of course, the dictionary in principle has a faster lookup with O1, while the lookup performance of a list is an ON operation. Dictionary map is key to a value and cannot have duplicate keys, whereas a list just contains a collection of values. Also, lists also allow duplicate items and support linear traversal. Okay, sounds to me like we want a two-dimensional dictionary. So we do have a test here, but it only goes to 70 bursts, so it's going to become useless once we go into the full solution, but we can still set up for now. So what is your setup? Test map. So our answer to this after 70 is 41 bursts. Oh wait, we do have 10,000. Never mind. We'll just do that. After 10,000, we have 5587. That's part one. Okay, so parse input, we're going to need to come out with a two-dimensional dictionary. And each dictionary is going to have integer, followed by a dictionary, which has an integer key and a Boolean. Okay, so first off, we need to get the array. It's going to be now, do we start with a square map? 1, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Yes. I'm not sure I want to depend on that, so let's just dynamically get it anyways. think it was drawing. Okay, so it's going to be new point. So if we have width of 3, then index 1 is the midpoint. If we have length of 5, then index 2. So it sounds like map width minus 1 divided by 2. And by what they've outlined here, I'm going to have to assume that our input's always going to have odd width and height. So that will work out. In fact, technically we don't need that minus 1, but let's just keep it in there. Also, we're going to need our dictionary. What did they call this? Grid computing cluster. Yeah, grid works. So for int I equals 0 is less than the input array length, I plus plus. So grid add. And so this will be I minus the midpoint x. And mine's blanking for a sec. A new dictionary. For int equals 0 less than input don't increment I, increment j. And then we need to figure out what the character is. should be good. Okay, so at this point, what we want to do is see if we can just replicate the grid. So that's going to be a list of int. Wasn't there a toList? Dealt with that recently. Okay, yeah. You just input into the parameters. But we actually want to do this in reverse order. Whatever. This is going to be. I don't want to flip it. You just flip the X and Y. That's another problem right there. I's not getting updated like that is. Okay, so we're getting it in. That's actually an input array. This is the Y. Okay. That's going to be IJ. I think that's okay. Y keys. Let's change these symbols just to be 100% sure that we've translated things. Maybe we should be okay, but... And underscore. Okay, let's try that out. Dictionary. So we had something a little screwy. Okay, put array. That old line end problem. We still got something going on there. There it is. So lock that up for now. Alright, so we need to do 10,000 infections. Or 10,000 bursts of activity. Do I want to put the loop in or out? Just do it here. So for it's less than 10, 1, 2, 3. So let's make infection grid global here. Okay, so first off, we can get the infected node count pretty. We should do a step for it. Virus first. So private. Let's go return void. Take anything in. So what do we call this little node? Carrier. Okay. Okay, so the position is going to be a point. Facing. Let's do our old facing struct. No, a num. Not struct. New point, say it starts at 0, 0. Begins in the middle of the map facing up. Yep. Okay. So what are our steps? First of all, if infected, turn right, else turn left. If current node clean, no, so flip current node. Okay, so not only do we need to check if this carrier exists, but we're going to have to, well, sorry, if it's infected or not, but we have to check if it exists. So first off, if infection grid contains key, false. It starts off uninfected. I think these are constant operations here. right now we're just turning directions. We don't need to worry about that. So if infected, turn right, else turn left. So that's all that. Helper functions. Right, so that's turning right. And for turning left, we're actually going to be a little cheeky. Because 2 wrongs do not make a right, but 3 rights make a left. Okay, so next up, we need to flip the current node state. That's pretty easy. But I am getting tired of typing this, so but we can't. Well, it'll help solve a little bit. So we just need another one of these. Instead of this, I'm going to do carrier position dot x, no, dot y, minus minus. Going right is going to increase the x. Down is going to increase the y. And going left is going to decrease the x. All right, and then after that, get infected node count. sec. So instead of console writing, we need a counter. You, and then at the end return the infection count. Right, we're on 22.1. Our test failed. Okay. $5,580. Oh, bursts will have caused an infection. Never mind, I'm counting the wrong thing. Oh, that's not going to help us. But we put it up here. Where do we put it? Yeah, we just put it inside the step virus. So if is current node infected. So we know this one is going to cause infection. So infection, burst count. We don't know if we might need that later, but we currently don't. So let's pretend it doesn't exist. You are not a function. Test passed. Answer is 5406. And that's the right answer. Oh boy, things are getting complicated. Okay, before I go too much further, I'm actually going to go ahead and... Well, let's read it, then we'll save part 3, or part 1, and then we'll get to work. As you go to remove the virus from the infected nodes, it evolves to resist your attempt. Uh-oh. Now, before it infects a clean node, it will weaken it to disable your defenses. If it encounters an infected node, it will instead flag the node to be cleaned in the future. Before it infects a clean node, it will weaken it to disable your defenses. If it encounters an infected node, it will instead flag the node to be cleaned in the future. So clean nodes become weakened, weakened nodes become infected, infected nodes become flagged, flagged nodes become cleaned. So we've got a nice for loop of 4. Every node is always in exactly one of the above states. Virus carrier still functions in a similar way, but now uses the following logic during its bursts of action. Decide which way to turn based on the current node. If it's clean, it turns left. If it's weakened, it does not turn and will continue moving in the same direction. If it is infected, it turns right. If it is flagged, it reverses direction and will go back the way it came. Modify the state of the current node as described above. The virus carrier moves forward one node in the direction it is facing. Start with the same map. And still with the virus carrier starting in the middle and facing up. Using the same initial state as the previous example, the drawing weakened as W and flagged as F. The middle of the infinite grid looks like this. The first 100 bursts, 26 will result in infection. Unfortunately, another feature of this evolved virus is speed. The first, that number bursts, that many will result in infection. Okay. So first of all, oh, and I didn't even have this up. So the puzzle. So instead of having a simple clean or infected, we're going to have 4 states. The methodology is going to change for the virus. This is the same as before. And we're going to do more iterations. So you don't exist anymore. Oops. So first off, let's save this. Solve 2017 day 22 part 1. Okay, so first thing we want to do here is we want to split this up. So we need a switch. Piece 1, we're going to do some of that, and what do we call this? Sporifica. Times was that? So we've got we've got thousands, 10 million. This is going to become actually, do I need to make a special input? No, I'm just going to be changing this from bool to an enum, so we don't need to worry about that. That's going to be the same, that's going to be the same, that's going to be the same. do that. Do that. We'll worry about you later. Did I delete you? I must have Control Z that. So you're gone. Okay, so that's step one. So next we need to come up with an enum. And so what do we have? We've got clean, weekend, infected, and flagged. Okay, yep. So that's there. You are now a node state. Aren't you happy about? Oh, okay. you're infected, then okay, so that should be everything. Let's just hide this for now. Make sure everything's working as we left it. 5406 was our answer. All tests passed. Excellent. Okay, so now on to part 2 proper. So we are going to copy this. All right, so our first step, decide which way to turn based on what we've got. So instead of this, if queen, turn left. If weakened, don't turn. If infected, turn right. If flagged, reverse. So these are going to stay the same, and then we need to figure out where we're going to turn. Oh, we actually want to... It just logically makes more sense for this to be here. Likewise, you're going to go there. So these we still want to keep as they are, and this is where we want to go. So if we're clean, turn left. Don't do anything, so let's just skip that. Infected. Flagged. Okay, so that's the first step. Modify the state of the current node as described above. So if we're clean, then oh, you become weakened, so we're jumping the gun here. Next, if we're infected, we need to flag it. So we don't need you anymore. And then move the carrier forward. Okay. Start with the same map. Still with the virus carrier starting in the middle and facing up. This is just sort of stepping us through. There's the speed. The first 10 million bursts, that many will result in infection. And 10 million bursts of activity, how many bursts cause a node to become infected? So for our test case, that answer is going to become much bigger. Okay. So check that. First part still works. Yep, looks good. Test case took a little while, but it's not anything too worrying. Okay, it's a little different from what we had in the test, but let's give that a shot. Hey, this is going pretty smoothly, knock on wood. Alright, so next up, close these down, update that. A22 part 2. Move on to day 23. Coprocessor conflagration. You decide to head directly to the CPU and fix the printer from there. As you get close, you find an experimental coprocessor doing so much work that the local programs are afraid it will halt and catch fire. This would cause serious issues for the rest of the computer, so you head in and see what you can do. The code it's running seems to be a variant of the kind you saw recently on that tablet. tablet? Day 18. Refresh my memory, but I'm worried this is Duet. It's Duet. The general functionality seems very similar, but some of the instructions are different. I don't care about what these instructions do just yet. Only the instructions listed above are used. The 8 registers here, named A through H, all start at 0. The coprocessor is currently set to some kind of debug mode, which allows for testing, but prevents it from doing any meaningful work. If you run the program, your puzzle input, how many times is the mul instruction invoked? So we're going to want to pull up day 18 here. Sounds like it's going to be different enough that we don't want to extract this out into its own class. But we will want to take liberally from it. Okay, so what do we got? We got set, which registers x to the value of y. Sub, which decreases register x by the value of y. Mul, which sets register x to the result of multiplying the value contained in register x by the value of y. And J and Z, which jumps with an offset of the value of y, but only if the value of x is not 0. Okay. So, no, let's... Yeah, okay, we'll do this. So many problems. Okay, first of all, let's clean up some of this. Just check for 18s. Okay. So first of all, seems to be running a variant of the kind you saw recently on the tablet. The general functionality seems very similar, but some of the instructions are below. Let's take a look at our input. So yeah, we don't have any send or receive, so let's delete that duet stuff. We don't need you. Play duet, we don't need you. We don't need you. We do need you, and we're going to change a lot of what's happening here. And we're going to need you. Okay, so first of all, we don't have a play command. We do have set, registers x to the value of y. Yep, okay, so that's the same. We don't have add. Do we have a sub here? No, so we don't have send or receive. We don't have recover. We don't have modulo. We got subtract. So that should just be flipping that. Multiply says register x to the result of multiplying it by the value of y. We've got set, subtract, multiply, and jump if not 0. We do not have any test cases, so this is going to be fun. I don't think the last one had test cases either, did it? These are all looking like I set them. Okay, so we don't have a set. Or sorry, sound. Subtract rejects. Sub. Register x by the value of y. Multiply still here. Modulo is gone. Recover is gone. And n. Okay, so match equals set. Add set. Multiply is good. Modulo and recover are gone. Okay, a constructor that takes 2 arguments. If not, then 0. Okay, that's happy. So that's our parse input. That's all good. So we need a mole counter. So let's just comment out this entire switch here. So we are going to Oops. Oh, just run. Alright, so we need an index because we're jumping around. We've got the global registry, I believe. Yep. So int index equals 0. Technically, we could jump off the low end too. Okay, so next, if command dot, oops. Let's define command first. Now, we're definitely going to need to know the multiply type. Are we going to need to know anything else? So this just did play and recover and jump. And otherwise we didn't care, so. And we also need to execute. And then index plus plus. So I think that should suffice. Three part one, yep. Test all passed. And we broke. No reference exception. We didn't set the register, did we? The registry. Six, 7, 2, 4. Is the correct answer. What's the twist? Now it's time to fix the problem. The debug mode switch is wired directly to register A. You flip the switch, which makes register A now start at 1 when the program is executed. Immediately, the coprocessor begins to overheat. Whoever wrote this program obviously didn't choose a very efficient implementation. You'll need to optimize the program if it has any hope of completing before Santa needs that printer working. The coprocessor's ultimate goal is to determine the final value left in register H once the program completes. Technically, if it had that, it wouldn't even need to run the program. Register H once the program completes. After setting register A to 1, if the program were to run to completion, what value would be left in register H? Wait, are we doing like almost nothing here? The switch which makes register A now start at 1 when the program is executed. Oh, you need to optimize the program. Okay. Well, first off, let's just clean up a bit here. Let's just confirm that we're still getting the same numbers. Yep. Okay, so first let's just take a look at our commands here. Very first, let's just see what happens when we run it. That happens. That makes sense. I haven't done anything yet. Okay, so first off, we want to do registry A equals 1. Okay, well, we'll put that in the background and we're just going to take a look at what we have here. So we've got set, subtract, multiply, jump if not 0. Doesn't look like we're going to be able to really optimize on this front. Okay, so I suppose what we're doing here is looking at the input and fixing it up. So jump not 0 A is going to be 1, so that never happens. Jump not 0 1, that's never going to be 0. I'll stop it. Okay, so that is what it was originally up there. Let's just take a look here. We're not going to remove lines, we're just going to nullify them because we don't know if there's going to be something that's going to tell us to jump back to this index. So first of all, A should not be getting set anywhere, and it does not. So, oops, I just said we're not deleting. 1 should never equal 0. So B set to 84, that's important because it's going to set C and then it's going to multiply itself. So B minus that. Oh, okay, so we can cut this out. Sub C, okay. And just as an aside, no. I kind of want to keep track of these variables, but let's just leave them for now. Let's make sure we demark that. So set F. F does not get used until we set F down there to 0. Set D to 2. D is getting used. Set E to 2. So GB, jump not 0. So jump not 0, it's going to jump back up here. So we're still good here. Subtract, so add 1 to E. Set G to E. Oh, hold on. We keep jumping back until G equals 0. And we're jumping back to this stage. Wait, it doesn't do anything, doesn't do anything. But B is going to change. Which we still got there. That's good. Eventually G is going to come out as 0. Set G to E. Then subtract B. Then jump, if not 0, out. So this would end the program right here. Wait, but that should be... In almost all circumstances, this should get us out. Where's H getting set? Right here, subtract H minus 1, so add 1 to H. So H is a counter for something. Okay, so this should never trigger, because this would end the program. Well, unless we jump back. This could be our exit point, so yeah, leave that there. Add 1 to D. Jump, not 0 G. Jump, not 0 F. Sub H minus 1. Set G to B. Substitute G, or subtract C from G. Jump if not 0 G. Jump if not 0 1. Oh, that never happens. Alright, I thought I might have had a jump if not 0 G2. Oh, I do. Right there. Yeah, so we keep that. Subtract from B, and then jump if not 0 1. That never happens. Wait. No, it always happens. What am I talking about? Jump if not 0, not jump if 0. Okay. So jump if not 0, A to 2. Well, that's our problem right there. Actually, hold on. What does jump do? Is it relative? Set of 2 skips, the next instruction. Offset minus 1 jumps to the previous instruction, and so on. Okay, yeah. So it's not go to a destination, it's jump relative. Almost want to set up a spreadsheet at this point. Okay, so this one, set B to 84, that's easy. Set C to B. Jump if not 0, A2. So A is not 0, so we jump ahead. Multiply B by 100. And then subtract minus 100,000. Negative 91,600. Set C to B. So right there we can skip that. Not that that saves us much. So set C to B. In fact, we could just reduce all this down here. So the first one is going to be set B negative 91,600. And set CB. Sub C minus, wait, add. So 84 times 100. 1, 2, 3, 4, 10, 400. Plus 17,000. We're skipping out on that. And we're skipping out on that. And we can actually skip out on these two. And so we're skipping out on that. And also that. So set F equals to 1, D equals to 2, E equals to 2, G to D, multiply G by E. So that could just be a set. Close the multiply. Subtract G, or subtract B from G. That's a lot. Negative 108396. notation is getting confusing here. Maybe I just shouldn't be doing that. So those we know get set later. We skip over that. This skips that. So we go straight to this, straight to that. We get that big number. Then we set C to B. And then we subtract that number from C. So that's that number. F is 1, D is 2, E is 2. G is D. Multiply G by E, that got us to 4. And then we subtract that. So now that's where we're at. Okay, so jump if not 0, G. Well, that's not 0. Subtract, so add 1 to E. Set G to E. Subtract B from G. So 3 minus 10, 8, 400. Negative 10, 8, 397. And G is not 0, so here's our first loop. So this goes back 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so that's our loop. So G is going to change. Let's just mark our loop for now. F is always 0. When did F become 1? Up there. Did I skip that step? Oh, because we jump. Well, it might get changed. E get changed. And that's it. Okay, so our first, or our second stage, we're starting here. You're starting at 1, and E equals 3. So then let's move forward. Set G to D. Multiply G by E. E could change here. So 6. Subtract B from G. Ten, 8, 3, 9, 4. G is not 0, so skip that. E, add 1. Subtract GB. Oh, sorry, set G to E. Set G to E. Subtract that. Negative 10, 8, 3, 9, 6. And that's not equal to 0, so we jump back. Okay, so what happens in the next loop? So set G to D. That's still 2. Multiply G by E. It's now 8. Subtract B from G. So that is going to be jump if not 0, G. Yep. Add 1 to E. Set G to E. Set G to E. Subtract B from G. Oops. And then jump back if we're not G. So this is decrementing G by 1 each time. Actually, I want those back because I'm going to need to do some of that. So this ultimately keeps decrementing G by 1 until we get to the point where G equals 0. So what's E going to look like when G equals 0? Well, E has to equal B. In the final loop, we're going to have So set G equal to D. Oh, sorry, 2. Multiply G by E. Oh, wait, hold on. Half that. Multiply G by E. So that's going to be 10A400. Subtract B from G. That's going to be 0. G equals 0, so we're going to execute the next line, which sets F to 0. Then we're going to add 1 to E. And then we're going to set G to E. Subtract G from B, or B from G rather. That's going to be roughly negative half that. So we jump ahead even further. Multiply that by E. That's a really big number. It's not that important. Subtract B from G, so that's going to be ish. Might be off by 1. G does not equal 0. So we jump ahead, subtract 1 from E. Set G equal to it. And then subtract B from G, brings us to 0. And we finally break out of this loop. So that's the end snapshot of that. Now we do have the potential to go back into that loop. And we're going to have to see what happens when we do that. Okay, so post loop, D equals 3. Set G to D. Subtract B from G. And then jump if G is not 0, which it's not. So the next loop is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so that looks like it's just going to do all that crap again. Which E is set to 2, G, F doesn't matter. D hasn't changed. So yeah, we can just get right back to where we are. So we're going to keep doing this for some amount of time. Does D influence at all? It's going to influence our starting point. That's it. Okay. So we can safely skip ahead for that. So we break through that loop. Get back here. We add 1 to D. Set G to D. We subtract, and we're back to where we started. So this is going to keep going until D equals 10, 8, 400. All right, F equals 0, so we ignore that. So next, add 1 to H. We do have one more negative jump. G to B. Subtract C from G. What was the number, right? Yep. All right, jump if G is not 0, so that jump if not. That should just exit us out. So we skip over that. So by this logic, at the end of it, H should equal 1. We set G equal to B. Subtract that. Oh no, wait, sorry, no, we skip, that's why. Gotta keep remembering that it's when it's not 0, not when it is 0. So we skip over that. And we add 17 to B. And then we jump back 23 spaces. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So F and D are also getting pulled into this. Okay, so we're setting E to B, so that's going to keep increasing by 17. just gonna set that. So see, this subloop will eventually set E to B. This subloop sets D to C, or D to B. This loop is going to keep going. So G will be 0 at the end of that. And what's happening with H? H is incrementing 1. So F's not changing, but will always get set to 0. Then G equals B, 10, 8, 4, 17. Subtract C. $16.93. G is not equal to 0, so jump ahead. Add 17. So we need to keep adding 17 until we get to this number. So if my theory is correct, then what we should get is 12, 5, 400 minus 10, 8, 400 and 17,000 divided by 17, which would be 1,000. So 8 should come out as 1,000 on the end. Answer is too high. Okay, well maybe we look at another route and we just try to short circuit these loops. So the ultimate thing here is we need to set G equal to B. So dot should be set G equal B. That's not what happens. Set something else. So first of all, set f equal to 0. E. So that's what that dot loop ultimately does. So next is that. Set E to 2, then do that loop again. So this one, subtract D from 1, set G to D, or sorry, add 1 to D, and keep going until G equals B, which means set D to B. So maybe that's just enough to go. So what would be the best point to modify this? When it's a string, or once we split it into an array? I think after we've gotten as a list of commands. Actually, what would be better here is if we can get a program to detect loops itself and then figure out what it does. No, that seems like it's going to be difficult. So this is only going to work for one input. But we only have to worry about one input. And once we've got the answer, we just scrap the program. We're done. Okay, so first of all, okay, so this loop, we can delete all these lines, and ultimately we're going to get these two lines. Okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 11th index is the first one. And this is, I think it's 8, 1, 2, 3, 4, 5, 6, 7, 9. We want this. Oh, we can only add to the end. We insert index and then item. Awesome. It's going to cut out a lot of it. So next, this part. Let's just get a copy of that. So this is now gone. Just to remember it by set F0. Okay, so next up, this does not interact with F or E at all. And that's just D equals B. Insert. I'm actually going to remove a little more. So I'm going to remove up here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have one large loop, but I'm not too worried about that. But I do need to update this jump. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. How far do we have to go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to cut all of that and dump it into Notepad just in case we made a mistake somewhere. All right, let's try it. And there's an error. We're missing a semicolon. Right there. Invalid cast exception occurred. Okay, subtract. Oops. So it looks like we're one off. Well, that's going. Let's make sure the jump's correct. So I said 12. We're skipping over I think it was there. So we want to get to F1, and we're skipping over from E2 until G minus 13. So we don't go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Did I make that negative? No, I didn't. And it still take a long time. First of all, let's just take a look at what we've got here. So what are our commands? What's the type of? Okay, so set, jump not zero, multiply b, sub, set, sub, set. Here matches with that. So this should be getting deleted. Yep. So this should give us 3 sets. And we got another jump not zero. Okay, we didn't delete enough. Did I leave that at 9? Oops, wrong file. I did leave it at 9. I wanted to delete a little more than 9. One, two, three, four, five. Yeah, and when that's smaller, that disappears. That's 10, 11, 12, 13, 14, 15, 16, 17, 18, plus 3 is 21. Still didn't like that. first let's check that. Set. We should have 3 sets. Yeah, okay, so that much is correct. So you are 0, 1, 2, 3, 4, 5, 6, 7. 20th, okay. Oh. Yeah, and then set jump distance. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, hold on. If we go 23, that brings us to 9, right? Yeah, so that brings us to 9. So 1, 2, 3, 4, 5, 6, 7, 10, 11, 12. That gives us 1001. Oh, no, I've been on the wrong screen this whole time. Crap. So since I've been apparently programming while you guys were blind to it, I'll just go over my answer if this is correct. Yeah, it was too high. So 1001. Yeah, maybe I don't have to do that now. Register A now starts at 1. The program is executed. Immediately the core processor will be so 8. Any hope of completing before it needs the printer? If the program were to run at completion, what value would be left in register H? So it's less than 1000. So what is going on here? Okay, well, those are our 3 loops. Let's just process this again. Oops. So we're going wrong. So A does not equal 0, so jump ahead, multiply B by 100. Subtract, so add that much, sorry. Set C to B. at 17,000. $12,500. Into our first loop, set F to 1, D to 2, E to 2, and now we're into our first loop. G equals 2, multiply it by E, subtract that, G is not equal to 0, so skip that. Add 1 to E. Set G to E. Subtract B from G. And then from there, G equal to D, which is back to that. Multiply G by E, which is that. Subtract. It's not, so don't jump. E equals 4. So G equal to E. Subtract. And then we loop again. And so eventually, D times E. So when we're halfway, that's going to set F 0. And then when we're the full way, I think it is. Subtract. Jump if not 0. One. Which is equal to E. Okay, so it will be that at the end. So yeah. Is there a universe in which f does not get set to 0? So what would need to happen there? So g would have to never equal 0 after these three. Which means we've got d times e and d is 2. Is it going to change? Will eventually get bigger. Minus b. Wait, e is always going to start at 2. And so this will actually happen if f can't equal 0, and there's a couple scenarios where that happens. One is where if that equation starts off greater than 0, and the other one is if the multiplier does not allow us to hit that. I'm not too certain if that last case is guaranteed to happen eventually or not. But okay, there is a scenario in which we skip f. So what do we do here? And yes, f is important. And that's why we're skipping half or so. Okay, so for dot, need to G starts at 0, so we don't need to worry about that. E to B, and set f to 1. Unfortunately, we don't have a free register. But we can cheat because we only check A once and we never go back. So I need to figure out if f is going to be 1 or 0. Actually, hold on. Let's analyze this. So once f equal... Oh no, we still don't know if we're going to skip some before we reach the halfway point. Hmm. So what does this ultimately mean? And that will actually continue for the rest of the loop. Of the greatest loop. Okay, so maybe we can leave that in. Well, unfortunately, we can't. Not without basically keeping it as it is. So ultimately, this is checking to see a very weird equation. We keep going through each integer until we get the so we're looking for factors, I think. Factors are something to do with primes. So if our end goal is h, what we should be looking at from here, we can just ignore this. Once we get f equals 0, we can skip over all this. So we just reduce that down in here. So sub e minus 1. Ultimately, what we think this is that set e to b, set d to b. So this is that we get out of there. I don't think we can do anything about D there. Can we? Two, three, four. One, two, three, four. One, two, three, four, five, 6, 9, 10, 11, 12, 13. So the 14th one. Gets up to 4. And then injured into 16, these two. EB, and jump 1, 5. So it's going to short that out a bit, but we're going to need something else, I think. I think I've got the wrong index now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Okay, so while that's running, let's try to find another short. Add one to D, and we have to do that to switch F again. Oh, should update some other jumps too. Fourteen, 19. Let's go minus 10. Has to go minus 15. Oh, but we have to add 2. Okay. Given that F, I'm not sure if there's anything else we can short. Because we only add 1 if we manage to set F to 0 during that round. Okay, at this point I'm going to have to sleep on it. We'll see if we can figure something out for Sunday. Thank you all for tuning in, and until next time, take care.